Yes, Jigyasa, now start sharing your screen.
Okay, sir. Yeah, sure. Good evening, everyone. Today we had with us Mr. Lalit Pant, founder and creator of Kojo and Kojo AI Managing Trustee. He is a code crafter, software architect, and a teacher based out of Dehradun. He has worked as professional programmer for many years, and he has designed and developed software for many companies in the US, Europe, and India. He holds multiple patents. His open source projects include Kojo, a programming language, Tefla, a deep learning toolkit, and many more. We welcome you, sir.
Thank you. Thanks a lot.
Thank you, sir.
Thank you, sir,
Well,
for joining, sir. I'm really thankful that you consented for this
It's my
session, sir.
pleasure. It's a
And
great
it
pleasure.
is, I would like to tell the participants that many of the speakers who have joined in this FDP, at the back end, it is Lalit sir and his team who is supporting us. Many speakers are there from his team who is guiding us in this FDP. Thank you, sir. Thank you, sir. Over to you.
My pleasure. Should I get going? Okay, so good evening,
yes, sir,
everyone.
please, sir. Please
Can you
continue, sir.
see my screen okay?
Yes, sir, screen is visible.
Okay, so I listened in on the previous session for the last 30-40 minutes, and that was a wonderful display of the kinds of tools that are available, especially uh, in the domain of a researcher in a university. My talk is going to be at absolutely the other end of the spectrum. It's going to be neural networks from the ground up, absolutely from the basics. And I just hope that that's not going to be wasted in terms of are there some people here who don't know much about neural networks, or is everyone very familiar with neural networks? Could I have that little bit of feedback, please? Are there people here who don't know much about neural networks? Okay, familiar, knowing basics. I'm gonna I'm gonna okay, not much. So at least there's one person who doesn't know much about neural networks. So even those who do, hopefully this is going to be a good refresher and a good revision. Uh, so so I'm not going to talk much about myself. Just a quick minute I'll take. BTech from IIT Kanpur, MTech IIT Delhi. I worked at various organizations around the world. For the last many years, I've been running my own NGO uh, in the area of children education, where we build this product to educate children with computational thinking and other essential skills for the future. And over the years, I've had the kind of privilege to have built different AI products using different generations of AI technology. So I have a whole, starting from symbolic logic, etc., down to now coming over to neural networks and deep learning. So that's been my journey. I will not spend much time talking about uh, the context in which we find ourselves today in this world, which is AI all around us, and with the prospect of the rate of progress of AI getting faster and faster. All of us know very well about that, so I will not spend much time on that. And then over the last year, of course, we know that generative AI has come in a big way, and it is starting to have quite an impact. I mean, the first impact of generative AI was, of course, on personal productivity, but now it's starting to have a deeper impact across industry in various sectors, uh, which I will also not dig too much into, because this was just meant to kind of set a context for our uh, dive into the domain of neural networks. I will talk about this larger context that I've been seeing over the last month or so, which is that people are now starting to say, and some are starting to worry that super intelligence is around the corner, and there's this danger of on the one hand there's a huge promise that, okay, if we have artificial intelligence systems which can, to begin with, let's say, do 90% of what any human can do in the area of intellectual work. So if those systems become available soon, then what impact is that going to have on society and on the economy and so on? So that's a large question looming in front of us. And one very good discussion around this has been done by the CEO of Anthropic, the company that makes the Claude large language model. So if you go over to his blog, it's a blog post called Machines of Loving Grace. So if you just search for Machines of Loving Grace, you will find a lot of information around this area. I think it's important for all of us to start thinking about these things uh, because maybe for the reason outlined in the next slide, which is borrowed from Rajiv Malhotra ji's book on AI and the Future of Power, which he wrote a couple of years ago, 2 3 years ago, I think. And that was pre LLM and pre generative AI. So this was like 3 years ago. AI was still much weaker than it is today. And he talked about 4 battlegrounds that are going to be looming in front of all of us in the future. And now these battlegrounds have been amplified 1,000 times with the increasing rate of the progress of AI. So these 4 battlegrounds are around economy and jobs, and that of course comes up right away when we start thinking about AI systems that can do, like I said, 90% of what humans can do in the area of intellectual work to begin with. Later on, robots will also come in, so they will start coming into the physical work also. But for the near term, if we just talk about intellectual work, uh, what kind of displacement will that cause? So there's going to be a battleground around economy and jobs, and then there'll be a battleground around countries that control the AI and their military might and their economic might, and how the world order is going to realign. So that is also something to keep in mind. The third area that Rajiv Malhotra ji talked about was psychological control and agency. So the previous speaker was also showing, models that could generate images, videos, and so on. So disinformation and creation of information that kind of kicks into the dopamine system of the human brain to kind of hook people into a narrative and a point of view. So that opens up many gates for psychological control and agency, where large masses of people are being controlled by some, corporates, potentially some companies around the world, who are tweaking the knobs of the algorithms that drive what becomes popular and so on. That is another area um, that's going to be a battleground. And the last battleground is selfhood, where with neural implants and uh, uh, things that modify the brain's perception of reality, that is going to get bigger and bigger in the coming times. So this whole perception, this whole area of how you perceive yourself, how you perceive the world, what experiences you have around the world, um, the experiences that you have in meditation, can you get that through some AI implant inside you, and how does that impact your spiritual progress, and so on and so forth. So that's another area that he's talked about. And I do think that in the coming times, these are going to be very important areas to keep in mind, especially with super intelligence around the corner. Okay. So that's kind of the backdrop for what we are talking about. And the fact of the matter is that this whole revolution is powered by neural networks. Okay, starting with one humble little neuron which can just learn very little, and then you can combine them to do more and more interesting things. And that is the journey we will take today in the time that's available to us. So we'll start with some core ideas in AI. and then we'll just dive into neural networks and look at how they work and what applications they have. And if I were to paraphrase the kind of intent of this session, I would say that we want to go from something very simple, the equation of a straight line, to something like face recognition, and then something like chat GPTs and LLMs, and building the foundation of knowledge all the way from the ground floor, one step at a time, so that we understand everything that's happening under the covers in all of these systems. Of course, we have very limited time, so by the time we get to face recognition and chat GPT, we will only kind of be able to give a glimpse into what's going on, but I will try to tie that to whatever we've learned uh, 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 for the during the earlier part of the session. Is everything going fine? Everyone is able to hear me fine?
Yes, sir. You are audible clearly, sir.
Okay, that's great. Okay, so so we are going to start with a very, very fundamental question. What exactly is artificial intelligence? Okay, and that's a matter for debate on various grounds, but we will keep it very simple and put up a nice and simple definition of intelligence to begin with. Because before we can start talking about artificial intelligence, we need to be able to define intelligence. And I'm going to say that intelligence is the ability to acquire and apply knowledge in useful ways. So the ability to acquire and apply knowledge in useful ways is intelligence. So then a working definition of AI becomes the ability of a computer system to do intelligent things. So the ability of a computer system to acquire and apply knowledge in useful ways. The essential ideas in this definition are the acquisition and the application. So the learning and the generalization from the learning. So these are two very important aspects of AI. So then, if we are saying that AI systems need to learn and then to generalize, a very fundamental question that comes up is, what do they need to learn? If they need to learn, what is it that they need to learn? And interestingly, there's a very simple and clean mathematical answer to that. They need to learn functions. In every very powerful AI application that you see out there, at the heart of that AI system, there's going to be a function. Okay, so that is the path that we're going to traverse. We're going to start with the idea of functions and start walking along that path, and then we will see how everything else emerges from that. So what's a function? I'm sure all of you know what a function is, but just to briefly define it, uh, at a very simple level, we can say that it's a box that takes an input and gives an output. So there's this box, you give it an input piece of information, and it'll give you an output piece of information. So that is the definition of a function. We have a couple of examples of functions here on the slide. So from a mathematical perspective, you could say that f of x is equal to m dot x, m times x plus c. So that defines a very simple function called f with a simple formula where you say that given an x as an input into that f, you multiply that by m and add a c, multiply by some given m and add some given c. And that is the rule that defines that, okay, this box, how does it produce an output from an input? And similarly, you can define that in coding. So that's the basic idea of a function. And here's that same idea amplified just a little bit more with some Python code. So we have, can you see the code? Is my screen visible big enough for you to see the code that's written here?
Yes, sir.
Okay, that's good. So m is 3, c is 1, def fx, return m times x plus c. And then we say x is a range from 1 to 10, and y is fx for x in x. Okay, so we define our input x and our output y, and then we we can look at that function from three perspectives. We can see the formula view of the function. So that is the formula view that defines what's happening inside that black box of the function. We can see a table view of the function that given some inputs, what are its outputs. And we can see a chart view where if the inputs and outputs are numbers, which they are in this case, you can plot them on a chart just to see how the input is mapped to an output. So before proceeding further, let's
Excuse me,
talk
sir.
about, yes.
Sir, please put it in slideshow mode.
Okay, that'll make it bigger. And
That
okay, that's better. Yeah, right. Thanks for the suggestion. So before proceeding further, let us look at some examples of functions in AI just to ground this idea of functions into practical things that you can relate to. So for example, there could be an earthquake prediction system where the function is a function from seismic data to the location and the predicted magnitude of an earthquake. Okay, or in an image classification system, it could be a function from images to categories. And let me make that more clear with the next slide. So, uh, in a classification system, you might have an image as an input going into the function box, and the output is a category for what is inside the image. In an object detection kind of a scenario, you also have an image going into the black box that is defined by the function, and the output is some boxes and some categories for things inside those boxes. Okay, so in object detection, a function from images to a set of boxes and categories. In image classification, a function from images to categories. Okay, in face recognition, there's a function from face images to semantic embeddings for that face, which are just a bunch of numbers that kind of provide a fingerprint, if I could call it, for that face, or a bunch of numbers that uniquely represent that face. So that's the function that's sitting there inside a face recognition system. And in something like ChatGPT, it's a function from some text to the next word that should follow in that text. Okay, so here are some examples. These are some examples of functions inside AI. Uh, so I hope by this point it's clear why functions are important in the context of AI. Right? Because it's the functions that provide the machinery for acquiring and applying of knowledge, or the learning and generalization of knowledge. So as per our definition of AI, functions are providing the machinery to do what we want to do in terms of learning and generalization. So the next question that comes up is that given that we need to learn functions, how do we do that? And that is where neural networks come into the picture, because neural networks are universal function approximators. They have the capability that they can approximate any possible function in this world. Okay, so that's their role in this whole scenario. And then to make neural networks learn functions, you have to train them using data with input and output pairs. You can think of the data for a neural network as a table, if you like, with input and output pairs. And then this data can be used to then train the neural network to learn the desired function. Okay. And this can be contrasted with functions in regular programming, where in regular programming, given an input, you have this function which you write, and then as per the logic in your function, some output is produced. So that is a regular function in software engineering. Uh, with functions in neural networks, that's kind of reversed or twisted around, where you have inputs and outputs, and and then the function is learned by the neural network through a training process. Okay, so any questions till now? Let me just see chat if there's anything there. Okay, fine. So, so next, let us look at the building blocks of neural networks, which are neurons. So I will not go into the biological neuron view of things. I will just look at the abstract view of the neuron that is used inside our computer systems. So a neuron is this thing that has incoming connections from other neurons, and every connection has a weight attached to it to define how strong that connection is. And then there is a bias in that neuron, and then there's potentially an activation function. So the way that this neuron works is that the inputs from other neurons come in and are scaled by the weights of the connection. And then if the sum of those scaled inputs is more than the bias, then the neuron fires. And then once it fires, its activation potentially goes through this activation function. It gets modulated through the activation function, and its output is then fed into subsequent neurons in the neural network. That is the basic structure of a neuron inside a neural network. Okay, so so now we come to a very important question that uh, given that neural networks are made out of neurons, what can one neuron learn? Can it learn something useful? And the answer turns out to be yes. And let's look at that. What it can learn is a straight line. That is, given some input, it can learn a straight line mapping of that input to an output. And that is kind of obvious given the fact that the neuron has two parameters, a weight and a bias. Every neuron inside it has a weight and a bias. So if y is the output of a neuron and the computation that is happening inside the neuron is y is equal to wx plus b, then the output is a straight line. So given an input, the neuron has the capability to learn a straight line with any kind of slope, any kind of y-intercept uh, based on the input that's coming in. So one neuron can learn a straight line. And that in itself happens to be quite useful because that is what linear regression is about. Uh, and in fact, this learning capability of one neuron is good enough to motivate the whole training process for neural networks, because the training process that we follow for one neuron is pretty much exactly the same as the training process we follow even for something like ChatGPT or the later models like O1 and O3 or DeepSeek or Claude or whatever. So models that are taking $100 million to train in the case of the American models, or $6 million to train for DeepSeek or whatever. The training process, the essence of the training process for those models is exactly the same as the essence of the training process for training one neuron to learn a straight line, which is what we will look at next. So here we have this scenario, which is actually borrowed from a real scenario that played out in the year 1800. But here I will keep it like a very simple scenario. So imagine that there's a planet that is moving across the sky. And on the first day, that is the position of the planet, the first blue dot. On the second day, the position of the planet is there. On the third day, the position is there, and so on. Okay. And now, at some point, we lose track of where the planet is, because maybe it comes very close to the sun and we lose track of where the planet is. So now the task before us is that many days later, can we kind of identify where in the sky that planet might be using the tools available to us? And so we have kind of formulated that problem in this particular way. So we've said that here are the different data points for where the planet was observed. And we want to fit this line we want to fit this line through that data through something like something similar to linear regression, because then through that line of best fit at any particular point in time, we will be able to predict where the planet should be. And then to do this, because one neuron is powerful enough to do this learning for us, we will start with one neuron and we will give it some random weight and bias. And then we plot what that neuron is predicting here as the orange line. And now our learning task for the neuron is to move this orange line over to the purple line. That is our learning task. Okay. And the way we do that is that we look at the differences between the predicted output from our neural network or our neuron, because our neural network has just one neuron. So we look at the predicted output from our neuron, and we look at the actual data that is available, and we identify the loss or the distance between these two, between the predicted and the actual. And then we sum all of these losses. And then our learning task is to minimize this loss by improving W and B. That is our learning task. And this is how we can go about doing this. So this is the essence of the training loop of a neural network, which we will refine further in the next couple of slides, but we are starting to look at the basic idea. So what we do is the following. So let's say we have a weight and a bias, a weight value of 10 and a bias value of 7. And let us say our loss is 50. Okay. So then what we will do is we will nudge the weight a little bit. We will make it 10.1, for example, and we will keep the bias fixed. And then we will see what happened to the loss. Okay. If the loss went up, which means it's a positive gradient, because if the weight went up and the loss went up, then the gradient or the rate of change of the loss with respect to the weight is positive. Then we know that we want to move W in the other direction because we want to decrease the loss. So then we kind of make the weight 9.9. We go in the other direction from 10, decrease it to 9.9. We keep the bias fixed. And then the loss goes down to 48, and we are happy with that. Then we keep the weight fixed to its new value, and we change the bias a little bit. We increase the bias, and we see that the loss has gone down. So that means that the gradient is negative, and we are happy with this because we want the loss to go down. And then in a loop, we keep doing this till we are satisfied with the loss, till the loss is small enough that we are satisfied with what we have. Okay, so that basically is the learning process of a neural network. So if we were to capture that in this little pseudocode algorithm, we could say that in the learning process or the training process of a neural network, we want to minimize the loss by improving the parameters of the network. So if we define GW to be the gradient of the loss with respect to the weight, which is the rate of change of the loss with respect to that parameter, and we define GB to be the gradient of the loss with respect to the bias, then the update process for the weights as part of the training process is that from the weight we subtract the gradient times a learning rate. And similarly from the bias we subtract the gradient of the bias times the learning rate. Okay. And we are subtracting because if the gradient is positive, you have to decrease the parameter, right? So that's why that subtraction is there. And this whole process is called gradient descent. And during this subtraction, we multiply the gradient by a learning rate to kind of control how much we move down the gradient. Okay. Because, so for example, if we plot the loss against the weight W, and we imagine that this is the loss curve, and we say that we were at point number 1 to begin with, if you change W too much during the gradient update, then we will go from point 1 to point 2. Okay, which we don't want to do. We want to, go towards the minima of the loss function. So this learning rate helps us control the kind of step we take down the gradient of the loss function so that we don't overshoot the minima and we settle in on an area that we like. Fine. And then we keep repeating this process till the loss is small enough, and that is our training process for the neural network. Okay, so now let's see these ideas in code. And before we do that, let me just spend a couple of minutes talking about uh, arrays and tensors or ND arrays. So in regular coding, you use just arrays as a data type for sequential data. For neural networks, we use tensors or ND arrays as a fundamental data type. And these have several benefits. They have more efficient memory layout. They have an arbitrary number of dimensions. They support vectorized operations, means that things can happen in parallel over the elements of the arrays. And then many more optimized numerical operations are available than in a regular programming language array. They work well with GPUs, so they become highly accelerated if you have a GPU available. And very importantly, they support automatic differentiation because, as we saw in the last slide, the knowledge of the gradient is essential during the training process of a neural network. And these tensors or ND arrays automatically support automatic differentiation. They support automatic differentiation. So that if a tensor is created through a bunch of operations with some other tensors, you can call backward on this, and then the gradients of all the tensors in that computation graph will be calculated. So these are some advantages of using ND arrays and tensors instead of regular arrays in the area of neural networks and deep learning. Okay. Now, as you start working with neural networks, the shape of the tensors that flow through the network becomes very important. But today we will be using this kind of a shape where we have two elements for every tensor. N is the number of different data points, and F is the number of features for every data point. And many times both these numbers will be 1 because we'll have one data point with just one number. Uh, but then sometimes we'll have multiple data points that we feed into our networks. So we will use a rank 2, we will be using rank 2 tensors most of the time. Fine, with the shape of number of data points and the features for each data point. And this will become clearer in just a moment as we start looking at things. Okay, so then let's do this simple linear regression problem. So first, let's just create the data. So we define M is 3, C is 1, F is M times X plus C, X is from 1 to 10, Y is Fx plus random uniform between -2 and 2. So just to add some random noise, because in real physical systems, there's always some measurement error. So just to simulate that, we add some random noise. And then we plot the data. So this is our regression data with the X here and the Y there. And now let us write a neural network and a training loop that will help us solve this problem. So here X and Y are regular Python arrays. So first we convert them to PyTorch tensors. Like we said, when we want to do deep learning or we want to work with neural networks, we always want to work with tensors or ND arrays. So here we convert the X and Y arrays into corresponding tensors. So the input data and the output data. And then we define a weight parameter and a bias parameter for our neuron in the neural network. And then we define a model function for the computation happening inside this neuron in our network. And the computation function is such that given an input, it just does W times X plus B. Then we define a loss function between a predicted value and the actual value. And that is the mean squared error of those two values. So, their difference squared and the mean of that, because we don't want the magnitude of the difference to play a role. We are interested in we don't want the sign of the difference to play a role. We are interested only in the magnitude of the distance. So we do a mean square error loss between the actual value and the predicted value. And then we define an update params procedure, which does what we saw in our algorithm definition a few slides back. So from the weight, we subtract some learning rate times the gradient of the weight. From the bias, we subtract some learning rate times the gradient of the bias. And then we zero these out so that the next time in our loop, we start with a fresh set of gradients. And then the training loop is very simple. For a predefined number of epochs, we do a forward pass through the model, given our training data, our input data. We do a forward pass and we get the predictions of the neural network. And then we calculate the loss between our predictions and the actual values. So that gives us our loss. Then we do a backward pass through the loss to calculate the gradients of the loss with respect to every parameter in the network. And then we update the parameters. So that's, very simple, straightforward training loop. And this is the exact same training loop that is there even in ChatGPT. So it's the same idea. And of course, there with something like ChatGPT, there'd be lots of bells and whistles and so on. But the essence of the training loop is precisely this. And then we test our model to see how it did. So we do, we say y pred is model function for the input x values, and then we plot the values predicted by our neural network in addition to the initial data over the initial data. And then we see that our neural network has learned a pretty nice line of best fit through this data. Okay, so so maybe I can, let me see. Let me just start this browser and let me start my Colab notebook in just a second. Okay. I think that's the tab which I want. So let me get it here. And I can get rid of this.
Sir, I have shared the rights with you again. Can you
Yes.
share the screen?
Apologies. I kind of closed the wrong tab by mistake. Can you see me now?
Yes, sir.
Okay, so we are back and the tabs are up and running. So hopefully we didn't lose too many minutes. Okay, so so we'll get back to seeing this in action in just a moment. Let's move on for a bit here. Then we'll come back and see things in action a little later down the line. And we are at 8:22. So, okay, so we still have 40 minutes. Okay, let's move on to what can one neuron with activation learn? Till now, what we saw was one neuron inside a neural network with a weight and a bias, but no activation function. Now we are adding an activation function into that neuron, and we want to see what new kind of thing it can learn on the basis of the addition of the activation function. And the activation function is going to be the ReLU activation function, which given some input A just does a max of 0 to A. Okay, so if the input is less than 0, then it returns 0. If the input is greater than 0, then it returns the input itself. That's what the ReLU function is. Okay, and here's a graph of the ReLU function. So it's a max of 0 and whatever input x is given to that function. Okay, so then the answer is that one neuron with ReLU activation can learn a line with a bend, because earlier it could learn a line. Now wherever that line is less than 0 for the y value of that line, it becomes 0, right? So so it's able to learn a line with one bend. Fine. Are we good? Can everyone hear me, and can you see my screen?
I think the screen is not visible.
Oh, I'm so sorry. Okay. Is it visible now?
Yeah,
Yes.
visible.
Okay, so let me just roll back a couple of slides. So we started to look at a neuron, which also has an activation function, which is the ReLU function. And that's what the ReLU function looks like. Okay. And then a neuron with ReLU activation can learn a line with a bend like that. Okay, so are we good? Can you see my screen and hear me fine?
Fine, sir.
Okay, apologies for this little hiccup there. Okay, so so now we come to the question of, so we've looked at one neuron with just a weight and a bias can learn a straight line. One neuron with a weight and a bias and a ReLU activation function can learn a line with a bend. Now let's see what two neurons in a layer can learn. Okay, so if we have two neurons, which are then connected to one output neuron from which the output of our network goes. So what can this setup learn? And the answer is a polyline with two bends, because each of these contributes a bend. And when you combine them through this other neuron with some additional scaling and some bias, then you get a line with two bends. Okay. So two neurons can learn a line with two bends. So here now we come to the essence of the matter, where we started our journey by saying that functions are the core things that we want to learn in AI systems, and neural networks are universal function approximators. Well, this is where it all comes together, where we see that n neurons in a layer can learn a polyline with n bends, right? So if two neurons can learn a line with two bends, if you just extrapolate from that, n neurons can learn a line with n bends or n plus one line segments. So if you have two bends, then you have three segments, right? So there's a bend here, there's a bend here. So there's one segment here, one segment here, one segment here. Similarly, with n bends, you have n plus one line segments. And we also know that any curve can be approximated with a polyline with n plus one line segments, right? So any given curve can always be approximated by small straight line segments, right? Given a sufficiently large n for that curve. So then, given these facts, any curve can be learned by a neural network with one hidden internal layer with a sufficient number of neurons, right? So if there's a neural network with this one internal layer, then whatever is the function that this guy has to learn, however complex is the curve that has to be learned, if you have a sufficient number of neurons here, they will learn a curve with uh, n plus 1 regions, which should be good enough to approximate any curve for any given sufficiently large n. Okay. Now, I would like to say one word about, or a few words about the deep and deep learning. So this whole area of deep learning comes in because it's much more efficient to have multiple layers of neurons learn your functions than to have everything in one layer. So k layers with d neurons each. If you have k different layers in your neural network, and each layer has d neurons each, then it can learn a line with d plus 1 to the power k segments. So there's like a combinatorial exponential increase in the learning power of a neural network uh, if you spread a given number of neurons across multiple layers. And this is where deep learning with many deep layer, many layers inside a deep network, this is where that comes in. And just as an example of that, a shallow network with 125 neurons has 126 segments available for approximating a curve, right? So if you have a neural network with one layer which has 125 neurons, then it can learn a curve with 126 segments. That is its learning capacity. Uh, a deep network with three layers of four neurons each has a capacity has 125 segments, because it's like four neurons, so 4 plus 1 to the power 3 as per this formula. So 5 to the power 3, 125 segments available for approximating a curve. So whereas here 125 neurons had the ability to had 126 segments available for approximating a curve, here 12 neurons have 125 segments available for approximating any given curve. So with much lesser number of neurons, you can uh, fit more and more complex functions if your neural networks are deep. So that is where the deep learning comes in. Before we start looking at some code, I think it's important to spend a few minutes talking about the flow of tensors through a neural network. So imagine that you have a tensor coming in that is two-dimensional. It's got an 2D data inside it, x1 and x2. And there's this neuron here with some weight and some bias and some activation function. And there's another uh, layer of neurons here. So the computation that's happening inside this neural network is that y is given by x times w plus b uh, going through an activation function, and then z is given by y times w2 plus b2 with some other activation function. So that is the computation happening inside this neuron. Same old idea, right? So weight times input plus bias, then it goes through an activation function across both the layers of neurons. So if we look at the dimensions or the shapes of the tensors flowing through this network, the shape of the input coming in is 1 times 2, because there's just one data point with two dimensions. Okay, so it's 1 times 2. Now the output here we see is 1 times 3. So it's still that one piece of data that came in, but now it's got three dimensions to it as it passes the first layer of the neural network. So the dimensions here are 1 times 3. So the weights here have to be 2 times 3, just to do the appropriate mapping from 1 times 2 to 1 times 3. The shape of the weights has got to be 2 times 3. And similarly, we see that the output is 1 times 1. So the weights here have to be 3 times 1 to do the appropriate mapping of 1 times 3 to 3 times 1, because the mapping that is happening is a matrix multiplication between the input and the weights. So when you do a matrix multiplication of 1 times 2 and 2 times 3, you get 1 times 3. When you do a matrix multiplication of uh, 1 times 3 and 3 times 1, you get 1 times 1, right? So that's how the tensors flow through the network. When you're writing code, this becomes very important to visualize, because if your tensor dimensions are mismatched, then there'll be some runtime errors and so on. Okay, so let's look at the big picture of So this is kind of a recap of what we've done in terms of how we train neural networks. So we want to train neural networks to learn functions, and the process that we use is called gradient descent. And the process is the following. So we randomly initialize some parameters for the weights. Uh, we randomly initialize the parameters or the weights of the neural network. Then we feed data through the network and compute the output. Then we compute the loss, which is the difference between the actual output and the predicted output. Then we determine how strongly each weight contributes to the loss. That is, for every weight in the network, we compute its gradient, which is the rate of change of the loss with respect to that weight. And this is done through a backward pass using the propagation algorithm to compute the gradients of the weights in the network. And then we update the weights based on how strongly they contribute to the loss, that is their gradient, in a manner that reduces this loss. So we saw that little formula, right? So W is equal, from W we subtract, if we look at that little formula there. So that's the formula, that kind of formula we use for doing the weight update, where from the weight we subtract the gradient times the learning rate. And we even saw that in code here, right? So from the weight we subtracted the gradient times some learning rate. Okay. So that was a textual description of the training process. And of course, the last step here is to repeat till satisfied. So you do this process till you're satisfied with your loss being very less. And then here's a code-based description of that same process. So given some input tensor and some output tensor for that input. So our tabular mapping of inputs to outputs, once that is given to us, then we create a weight and a bias for our network, and the shapes of these weights and biases can be whatever is appropriate for the network. And then for every epoch in our training loop, we call the model function with the input data given to us to get the predictions of the network for that input data. And this is the forward pass. Then we calculate the loss using the loss function, uh, which calculates loss based on the difference between the predicted values and the actual values. The actual values are given to us when we want to train the network. The predicted values come from the model, from our neural network. So we get the loss. Then we do a backward on the loss to compute the gradients of the parameters with respect to the loss, uh, or the gradient of the loss with respect to the parameters. And once the gradient is known, then we update the parameters. So that's a standard training loop that we use. Okay, so I think now we can go and do a little demo here. Okay, we are connected. So let's see. So let's do linear regression. So this is our code to set up our training data, and then we plot the data to see that, okay, uh, this is the data through which we want to fit a straight line. Then we convert our given arrays into tensors. And this is, of course, on Colab running using PyTorch. Then we define our weight and our bias for our neural network. The shape of the weight is 1, 1, so there's just one weight and one bias because we have just one input going through one neuron. And here's a pictorial representation of that. The input is coming into this neuron, which has a weight and a bias. And there's no activation function, so the ID activation function is used here. And then here's the code that maps to that visual representation. So the model function is just W times X plus B. This is the computation being done by the neural network. The loss function is the mean squared error loss given the predicted value and the actual value. And then the update parameters procedure is what is very similar to what we saw in that slide. So it's that same procedure. So let me just define these things. loss function, update parameters, procedure, and then we have the training loop. And then we can plot the outputs of the network. And the network has done a pretty decent job of uh, learning from the data that was given to it. So this was linear regression. Now let's try nonlinear regression for a much more complex function, you know, much tougher function to fit within a limited amount of time. So it's an elbow function. So we define the data for that function, and then let's plot it to see what that function looks like. So that is what we have to fit with our neural network. So we convert the arrays, the input data arrays into tensors, like we said that we always want to do. And because this is a slightly more complicated problem, we will have to normalize our data so that the gradients that flow through our network are numerically not too high and they stay stable. So we will normalize our data. So we compute some statistics for our data, and then we kind of normalize the input data and the output data just to bring down the numerical values of things flowing through the network so that the gradients remain stable. Okay, then we define the parameters of the neural network. One set of weights and a bias, and another set of weights and bias. Okay, so here we have this structure for the neural network. We have the input coming in. We have multiple neurons in our hidden layer, and then we have one output layer. Okay, so for the hidden layer, we have the shape of weights, which is 1 comma hidden. Okay, so that is the required shape to transform a 1D input into a 4D output coming out of the hidden layer. So we do the appropriate shaping of the weights, and each of these has a bias. So there's a hidden number of biases. And for weight 2, we have the shape hidden comma 1, because the hidden number of outputs have to now be converted into one output from the network. The outputs from the hidden layer have to be converted into one output from the network. So from hidden, we come down to 1 as the weights of this the neuron in the output layer. And then it's got one bias. So we've defined pretty much our neural network. And then we define the model function corresponding to this picture. So the model function is doing x matmul w plus b1. So matrix multiplication of the input x with the w matrix here plus the bias matrix here. So that gives us L1. And then we are using the ReLU activation function. So we take L1 through the ReLU activation to get the L1 coming out from here as output of the hidden layer. And then L2, which is the output of this neuron, is L1 matrix multiplication with W2 plus bias 2. So W2 and bias 2 are the parameters here. So that is our model function. The loss function is the same as before. The update parameters procedure is the same in spirit as before. It just has more parameters to deal with. So it's just doing a little more work, but it's the same idea. And now the learning rate comes in as an input into this procedure. So it's using that provided learning rate to do the update of the weights. And then the training procedure is exactly the same. Okay, so we've done our training, and then let's see what we've got. So we plot the results of our model. And we see that it's not quite done a good fit through the data that was provided. So let's go back and let's run another set of rounds of training, another bunch of epochs. And now let us see what the position is. Now it's done a better job of learning a kind of a curve through the provided data. So that is nonlinear regression. The key thing in nonlinear regression was that we needed to have a hidden layer. Without the hidden layer, we would not be able to fit something that is not linear. Okay, so let's go back to Back to our presentation, to our slides. Okay. So now we are moving on from regression to classification. In regression, we've seen linear regression, nonlinear regression, and regression is just this process of learning any function with some continuous input and some continuous output. So we've seen how that works for both the case where we want to learn a straight line or we want to learn any curve. We've looked at that. Now we're going to move on to classification, which is the next set of problems uh, that come up in the area of AI. Any questions on what we've done till now? Let me look at the chat if anything's there. Okay, so there's one question at least. Oh, fine. To train the model, many people use PyTorch instead of TensorFlow. Why is it so? Could you kindly elaborate on it? As I feel at least. Okay, fine. That's a very good question. I'm going to say that. So TensorFlow 1, when it came out, had this static graph based model of kind of computation where you had to separately define this computation graph for your neural network and then do the training, etc. on it. So the programming model was relatively difficult. And then when PyTorch came out, it turned out to be something where programming neural networks was much, much easier in PyTorch compared to TensorFlow 1. And by the way, I hope everyone can hear me fine and see what I have on the screen fine and so forth. I will share the collab notebook. I will do that. Can you guys hear me fine? If you could just give me a heads up, then I will keep going on. Can you hear me fine, see my slides fine? Okay, so
Yes,
there's
sir.
there's a yes, so that's good. Okay, so when PyTorch came out, it made things much easier. Then TensorFlow 2 came out, and then they had this Keras programming layer, which made things uh, much easier than TensorFlow 1. But by then, PyTorch had become very popular, and uh, and even to this day, even though TensorFlow 2.x provides a very simple way to do neural network training now, if you want to customize things, they are more difficult in TensorFlow 2.x, whereas PyTorch makes it very easy to customize things because it is very Pythonic. You know that there's no there isn't this static graph thing underlying under the covers which we have to work around, etc. Even with a higher level API. So I think that's kind of in very brief. You know, it's a huge area with lots of arguments plus pros and cons. But that's why PyTorch is being used more and more. Okay, so let's see. There were many questions there. Why pandas? You know, it's pandas is a great data frame library for structured data. You know, you can just load the data, and you have a lot of functions to analyze things. It's very robust, very old, very strongly used. So it's a good tool for kind of data analysis. I will share the Colab notebook. Is it possible to discuss the tensor dimensions? Yes, definitely. That is very important. Mm, we have just 15 minutes left. So maybe what I'll say is that we might not have too much time to go very deep into the dimensions because I want to give you a flavor of things right now. And then we can, you know, dig deeper at some point as required. How to optimize ML model for various input parameters. So there are two things here, right? One is that what is the structure of your model? What is the architecture of your model? That is something that you have to do either through, you know, experience or expertise or using some tools. Once your model is defined, then the training process is like we said, you know, it's like the gradient descent based training process. It works exactly like we described earlier in our talk today. Any difference between abilities of TensorFlow and PyTorch? No theoretical difference. Yeah, just practically you might find one easier to use than the other. Is it possible to discuss on mail? Yes, absolutely. So you can just write to me. Mayank sir has my email ID. So you can absolutely get in touch with me. Okay, let's move on. Uh, with classification, the problem is to, as opposed to regression, in classification, problem is to take an input and classify it into a category. And the input could be n dimensional, and you could have C outputs for each possible category that might be present in that input that's coming in. So we will look at two different things. We look at binary classification with 2D input and one output. And even though there are two categories in binary classification, one output is sufficient because that output can tell you the probability of the first category, and then the probability of the second category is just 1 minus the probability of the first category. And then we will look at multi-class classification with 2D input and 4 outputs or 4 classes. And here the outputs represent the probabilities of each of those 4 classes. So there are 4 outputs, and when you feed some input in, all those get some numbers, and then whichever is the maximum one, you can say that that is the predicted category for that input that's coming in. So for binary classification, here's the sample problem we have. We have 2D input data coming in. So there's 2 dimensions to this data. And then we've plotted that data against the category of the data for any given X and Y. And we see that we have 2 classes, class 0 and class 1. And to solve this problem, here's the kind of neural network that we use. So here's the 2D input coming in. And then here's a neural network with 2 weights, W1, W2, and an activation function. Okay. And then the computation carried by the neural network is the following. It does the good old matrix multiplication of the X with the W. Okay. So that gives us the first part of the computation. And then the output of that computation, it goes through this function called the sigmoid function, which is defined here. Okay. So in effect, the network is doing this computation that's given at the bottom. So X is multiplied with W, and then that is given as an input into the sigmoid function, and that is the probability that's coming out. Okay, the sigmoid function looks like this. If the input to the sigmoid function is 0, its output is 0.5. As the input to the sigmoid function grows, very rapidly the output approaches 1. As the input falls, very rapidly the output approaches 0. Okay, so that's the property of the sigmoid function, which makes it a good function to represent probability. Okay, so that's the computation that's happening in this neural network. And we will dig deeper into that. We'll dig deeper into what's maybe let's just go there. So what we want to do actually with this, on what factors does the choice of the activation function depend? On the problem that is there, and for different families of problems, the activation functions are pretty well defined. So for binary classification, the standard activation function is sigmoid. So what we want our network to learn is this line. Okay, this is the decision boundary between class 1 and class 2. So we want the network to be able to learn this line so it can classify easily across class 1 and class 2. And the way that it does that is that it learns values of W1 and W2 such that W1 times X1 plus W2 times X2 is equal to 0. Okay. Because when the output of that matrix multiplication is 0, and that is fed as an input into the sigmoid function, the output from the sigmoid function is 0.5. Okay. So if the output is 0.5, that means that on this line, the probability of any class is 0.5. So this is the decision boundary. On this side of the decision boundary, the probability of one is going to be more. On this side of the decision boundary, the probability of the other one is going to be more. On the decision boundary, the probability is 0.5. Fine. So that's how this thing works. It has to learn W1 and W2 so that X1 W1 plus X2 W2 is equal to 0, given the input data. Okay. So the training loop happens to be exactly the same, just re-emphasizing the point that that we are making, which is that once the neural network is defined, once its model function is defined, once its loss function is defined, once it's defined how you update the parameters, then the training loop for the neural network is exactly the same across all kinds of neural networks. In concept, it's the same thing that happens inside a neural network training loop. So you have the forward pass, then you calculate the loss, then you do the backward pass, then you do an updation of the parameters. Fine. So that's the training loop. And let's talk a little bit about the loss function here. For linear regression, we saw that the loss function was mean squared error. Here, the loss function is the binary cross entropy or the regular cross entropy. That is the loss function, the standard loss function for classification problems. And the basic idea with this loss function is that it's the negative log of the predicted probability of the actual class. So, uh, let's see if I have a diagram here somewhere. So, let's say this is a classification neural network. Okay, and some input is coming in, and these probabilities are getting predicted. So for a given input, if the actual output is the second one here, if the actual category is the second one here, then to calculate the loss of the network, we will just look at the prediction of the network for the actual category. Okay, that is what this statement is saying. So the loss is the negative log of the predicted probability of the actual class. Okay, so whatever is the actual class, you see the predicted class of the network for that actual class, and then you do a negative log of that. Why do you do that? Well, there's tremendous amounts of theory behind that, but one very good property that we can see is that if the predicted probability of the actual class is 1, then the loss is 0. So if the actual class is 1 and you predict that that is the class, your probability for that class is 1, then the loss is 0. So here, if the prediction is 1, we see that the loss is 0. If the predicted probability of the actual class is 0, then the loss is infinite. So if the class is actually present and you predict its probability to be 0, then this loss function predicts a loss of infinity. So the loss rises up faster and faster as the predicted probability moves away from 1. So the probability should be 1, and as you move away from 1, the loss rises faster and faster. So this is a good loss function. Okay, and this is the loss function that is used for classification. Fine. So that was binary classification. Am I going to get 10 minutes extra maybe? Because my session started 10 minutes late. Anyway, we'll keep going on.
Sure, sir. No problem.
Okay. So before we do the hands-on for this, let's also look at multi-class classification. So so with multi-class classification, I mean, the data pretty much tells us what's going on. So we have two dimensions in our input data, x1 and x2, and then the x1 and x2 values cluster in 4 different categories. So we have 4 different classes that are present in the data, and we have to get our neural network to kind of learn a classifier for this data. So multi-class classification is based on a function from n dimensional input to c outputs. Here we have 2D input and 4 outputs. The multiple outputs have the following properties. So in a classification neural network, the outputs of the network have the following properties. They're all positive, they are less than 1, and they sum to 1. Okay, and this is ensured by the activation function that is used in the last layer of the neural network. And with these properties, the outputs can be interpreted as probabilities. Given these properties of the outputs, we can interpret them as probabilities. And here for multi-class classification, this the sigma, the softmax actually, the softmax function, not the sigmoid. So the softmax function is used to compute the outputs. Okay, so we are into the demo now. Let's look at the demo. So first, let's look at binary classification. We have some X data, which is two-dimensional, input data, which is two-dimensional. Then we have the categories for that input data. And if we plot it, we see, that's what our data looks like. So we have two classes which are linearly separable. Then we create a neural network uh, to be able to do this kind of classification. This network has two inputs coming in, 2D input coming in, and it's got a weight and a bias. The shape of the weight is 2 times 1 because it needs to put out one output, which is the probability of class 1, and it's got one bias. So that's a network. Then corresponding to the diagram, our model function is broken into two parts. One is before the sigmoid and one is after the sigmoid. So before the sigmoid, the computation that happens is x times w plus b, the same old regular computation inside a neural network. So that is the model logits function. So these outputs before the sigmoid are called logits because they are kind of like the logs of the probabilities. And then the model function first calculates the logits and then feeds the logits through the sigmoid to compute the function carried out by the whole model. And the loss function is the binary cross entropy loss between the predicted value and the actual value. The update parameters procedure is very similar to before, so let's also keep running these. So loss function, update parameters procedure, and then we run the training loop. And then we plot that decision boundary. We see where the model has found the decision boundary. So we have some helper things here to plot the boundary. So we plot it. And we see that this is the decision boundary that our network has learned, which is pretty good. So our network did well on this problem. Now let us look at multi-class classification. So we take some data, put it into tensors, we normalize the data, then we plot it, and then we have our data which is in 4 different categories. Then we define the parameters of the neural network. So the weights are 2 to 4 because from 2 inputs we have to go to 4 outputs for the 4 possible categories, and there are 4 biases. So we define the parameters of our network. Then the logits function does something very similar to before. And the model function also does something very similar to before, except that instead of sigmoid, it uses the softmax function. So for binary classification, the activation is sigmoid, and for multi-class classification, the activation is softmax. That's like these are well-defined activation functions for classification. And then our loss function is cross entropy, which is very similar in spirit to the loss function that we talked about. And then we have the update parameters procedure, which is doing exactly the same thing as before. And then the training loop is also exactly the same as before. So once we do that, we have this function to plot the boundary for us. And we plot a decision boundary. And we see that it's done a decent job. It's come up with a good decision boundary for the 4 categories available to us. All of this has happened live in real time, right? With the networks that we've defined and the training that we've done. Okay. So we looked at multi-class classification. Then let's do a quick demo of face ID, uh, so let me actually run a demo first, then we'll talk about what's going on. So let's see. Okay, code is right here. You can see my screen fine?
Yes, sir.
Yes, sir.
Okay, that's good. This is inside my Kojo environment for children of all ages, basically, because you can do very complex things inside also. So we're running this little script here, and it's using a PyTorch model under the covers. I have to shut down my video here. So let me shut that down and run it again. Okay, so there we are. So what I can do is I can learn my face. And then if I verify it, and if it's the same face, it's going to be green. And if it's going to be a different face, for example, if I hide it, it's going to be red. If I turn my profile, then let's see, it couldn't recognize that much of a profile. If I turn a little bit in this direction, didn't recognize, turn a little bit this way, then it said it's the same person. So that's the application I'm talking about here. uh, so the way that this works is that there's this model uh, available to this application. And what this model does is that given any face, so here's kind of a pictorial representation of the model. Given any face, and in fact, even before I tell you what it does, let me tell you that this was trained against a face database of, let's say, around 8,000 to 10,000 people. And the idea with that project was to be able to classify any of those people. So once you train on 10,000 people, if you have a new image coming in for any one of those 10,000, you should be able to say that this is that person. So that was the context of the training of this model. Now what we have done is that we have lopped off the last layer of the network, and we have kept the second last layer, because all the information needed to do the functioning of this network, all of that knowledge is there in the second last layer. The last layer is just doing the final thing to classify faces based on all the computation that has been done inside this deep neural network. So for this particular application, because my face was not there while this thing was being trained, so we are lopping off the face classification layer of this model, of this neural network, and we are keeping the second last layer, which has a size of 2048, or the version I'm using is like 512. So there are like these 512 numbers which can be called a face embedding. So embedding is just a good representation of something. So these are some numbers that nicely represent that face. So when we feed an image through the network, we get back these numbers that nicely represent that face. So then to right, to run this application, what we do is that when you run the program, it starts a webcam feed, and then it identifies where the face is in the feed. And then when you say learn, it takes a picture of it takes a kind of a sub image of the face portion of the whole image, and it feeds it through the network, and it gets those embedding numbers for that particular face. It saves those numbers somewhere, and then it's ready to start verifying. So then when somebody says verify, the same process is done, and another set of 512 or 2048 numbers are retrieved, and then the original set of numbers are compared to the new set of numbers, and if they are close enough, then you say it's the same face. If they're not close enough, then you say it's a different face. Okay, so that's how that works. But the basic idea is that everything we learned about classification, that still totally applies here, because when this model was trained, only difference was that it was trained on maybe 1 million images, or 50,000 images, or whatever. Let's see, maybe it's defined here. uh, Whatever, so some large number of images it was trained on, but the essence of the concept was the same. So each image was some size, so the dimensionality of the input was quite high. And then instead of 2 or 4 categories, there were like 10,000 categories in the output of this network. but the concept of what was done was exactly the same as the kind of classification that we did, and the training loop must have been very, very similar. So it's the same concept that we learned that is now being scaled up and applied in a much bigger application. And this is a demonstration of that aspect of things. Okay, so then on to the last piece of the puzzle for today, which is ChatGPT or LLMs. And this also works through a very classification like neural network, where the input is your prompt, whatever is the prompt that you've given in. So that is the input into this network. And the output is the classification probability of the next word out of a category of words from a vocabulary. Okay, so it's a classification problem. You have a vocabulary of, let's say 30,000 words. The actual details are slightly different, but just let's say that there are 30,000 words in the vocabulary. Then the concept is very similar to what we saw earlier. In our case, we just had 4 possible outputs. But so in our network here, we had 4 possible outputs. Now we have 30,000 possible outputs, which represent the probability of the next word given the prompt. Okay, and then you can pick that word, and that gets fed into the next input into the network, and then the next word is predicted, and the next and that gets fed into the input, and so on. So at the end of the day, these models, these LLMs, are just next word prediction. Okay, and the inside details are of course much more complex, and maybe I don't have time to go into that today. Uh, uh, but if you can just take this idea away from here, that there's some input coming into this network, and the output is just a bunch of probabilities for words from a vocabulary. So that helps the network to determine, or the model to determine, the next word, and then that is fed in as the next input into the network, and then the next word is determined, and so on. So word by word, the output from the network is shown to you. Okay, so I think that's my talk for the day. If we do a quick recap, we can say that we saw that function learning is a core task in AI and machine learning. And this can be done very nicely through neural networks, which are universal function approximators. Network with n neurons can learn polyline with n plus 1 segments. So any curve or function can be approximated by a neural network. Now, if a neural network is deep, then the learning and approximation can be made much more efficient. So that is the rationale for deep learning. One can train any neural network using gradient descent. Then you have regression problems, you have classification problems. And we saw 2 pretty big applications of classification problems through the Face ID verification thing. And we talked about how ChatGPT also uses a classification like network to do its work. Okay, so that's it from me. Let's see if we have some questions on chat. How many epochs are required for training a DL model? It depends on the problem and the data. So in our case, we were, doing something like, let's see. So if we were to say that maybe this was the toughest one that we did, so we did 1,000 epochs. So for smaller problems, 500 to 1,000, 2, 3, 4,000 is good enough. For much larger problems, it depends, because if you have a lot of data, then maybe 3, 4, 5, 6 epochs is also quite good, because then you're doing stochastic gradient descent, feeding in multiple batches of data. And if you have millions and millions of pieces of data, then the network gets to see the data many, many, many times, even in one epoch. So there, even, 5, 10, 15, 20 epochs might be good. Sometimes for very big ones, even 2, 3 epochs might be sufficient. So it will depend on the problem and the amount of data and the complexity of the model. how to go about learning multi-class classification for image data set. I mean, I learned these things a long time back. So actually, I'm going to say that if you really want to learn these things, and this is very old advice, maybe there are better things now, but Andre Karpathy, who was, the one of the original people at OpenAI, he was the director of AI at Tesla also. Then he went back to OpenAI. Then he's doing something else, doing a startup now. So when he was at Stanford, he did some very good courses on deep learning and computer vision. Uh, and if you want to deal with an image data set, so I think it's CS231N or something. That's the name of the Stanford course. And I saw the 2015 or 2016 versions, but every year they have a new version. The 2015 version would still be very good, because the fundamentals are still the same. So if you want to really dig deep, that would be one good suggestion. Other than that, I'm sure if you do a search, whatever is hot these days, that'll pop up for you. But that course will build a good foundation for you. Okay, so I'm kind of done with my session. Any further questions? Feel free to email me or WhatsApp me. So you can write to me at pant.lalit@gmail.com or lalit@kogics.net. Lalit@kogics.net or pant.lalit@gmail.com. You can write to me. I will say that, given this larger context, over the last 10 years, a lot of my time has been spent building this platform for children to learn coding and computational thinking, etc. But now I'm seeing that AI is getting more and more important. So it's time for me to maybe spend some more time doing some more products in this area, or in some way contribute to this area, especially for the Bharat mission of, uh, because like we said, it's like a geopolitical, there's a geopolitical aspect to it also. So I definitely want to see how I can contribute to this whole AI initiative in terms of building technology or building frameworks or building applications or whatever. Now, so if anyone wants to contribute, collaborate on any ideas where you want to do some interesting things with AI, I'm very open to collaborating and or mentoring or anything in that spectrum. Let me put the number here so that it's easily available to you. Okay, so you can get in touch with me on WhatsApp or via email. I'm always very happy to, if nothing else, just discuss ideas or hack on things or just do some fun techie discussion. I'm very game for any of that. Okay, thank you very much. Bye-bye. See you.
Thank you so much, sir, for your wonderful session. Now, on the behalf
My
of
pleasure.
everyone, I would like to express our sincere gratitude to Mr. Lalit Pant for his insightful session on learning neural network. Your expert knowledge and clear explanation have greatly enhanced our understanding for this complex topic. We truly appreciate the time and effort you took to share your expertise with us today. Thank you once again, Mr. Pant, for such an enriching experience.
My pleasure. Thank you.
At last, I would like to thank the organizers and participants for their valuable contribution. We also appreciate the active engagement of all attendees, which made this event a great success. Thank you, everyone.